Hi, we're going to be taking a closer look at single replacement reactions and showing you how to predict what the products of those single replacement reactions would be if you were not given the product, if you were only given the reactants, being able to figure out what would happen with that reaction. There will be times when this will stop and I'll give you a chance to write some notes down. Please take that opportunity to do that. It will be helpful for you. There's also a document linked that will give you a table that I am using in this video. That table is sometimes handy to have available with you when you're doing this. Okay. All right. So let's first review single replacement reactions. Just so that you're aware of what's happening here. In a single replacement reaction, you have a single element that is going to try to replace an element in a compound. So when you look at the reactant side of these reactions or the left side of these reactions, you will always see a compound dissolved in water or aqueous, and then a single element, okay? And then the same thing will exist as on the product side. You'll have a compound and a single element, but they will have changed. Okay. So a couple things to keep in mind. First of all, if the single element is a metal, it will be attempting to replace the metal in the compound. So for example, our single element is zinc. Zinc is a metal. This metal will try to replace the metal in this compound. So in that case, it's copper. Okay, so the zinc, the metal will kick out the other metal. You cannot put two metals together. So we can't combine zinc and copper. One replaces the other. If we are doing a reaction in which the single element is a nonmetal, so let's say, for example, this was fluorine. If the single element were a nonmetal, then it would be attempting to replace the nonmetal or the anion in the compound. We'll show some examples of that later. Okay, I'm gonna go ahead and close this window here. The single element will only replace another element if it is more reactive than the element it's trying to replace. Let me clarify that for you. The single element, in this case zinc, will only replace another element, copper, if it is more reactive than the one it's trying to replace. So in this case, in order for this reaction to happen, zinc has to be more reactive than copper. Okay? Zinc has to be more reactive than copper in order to be able to replace copper. If you think back to the Edpuzzle you did, that he compared this reaction to a dance in which you have a dance pair, a couple dancing here, and then this one, the single person comes and tries to cut in or replace one of the dance partners. Okay? So if you want to think about it this way, the only way that zinc is able to replace copper in this dance is if the nitrate is more attracted to zinc. It's more reactive. If zinc is more reactive, it can kick copper out. If not, then copper is going to stay there dancing and zinc is just out of luck. Okay, and I'll show you a couple more examples of this as we go along. This is a picture of the table that I have linked on this assignment. You can print this off. You can kind of keep it handy, save it to your computer. It's very helpful to have. This is called the reactivity series, and it's a look at all of the metals in order of their reactivity. The most reactive metals are at the top, and then they get less reactive as you move down. So you'll notice potassium is the most reactive metal up there at the top, and then platinum, the least reactive metal, all the way at the bottom. One thing I want to point out to you though, right in here is hydrogen. Hydrogen is always listed in the reactivity series as a metal, even though it's not a metal, because it forms a positive cation, just like metals do. Because remember, it's on that left-hand side of the periodic table with the metals, and it forms a +1. So it's going to be listed with the metals and it's going to be used just the same way. Okay, so here's the reaction we had before in that example. Zinc trying to replace copper. So if we look at this table, here's zinc and here's copper. Zinc is more reactive than copper, so it's able to kick copper out. So here's copper kicked out by itself, and zinc has now become part of the aqueous solution here. And I have a video of this reaction that I'm going to show you so you can see it happen. Now, this copper 2 sulfate solution right here, this is copper 2 sulfate dissolved in water. So there's copper ions and sulfate ions dissolved and floating around in here. And then we have our solid zinc.
What? Let's find out.
Oops, I want to do that. Sorry, I just wanted to point something out to you. Okay, so when we put this piece of zinc into the beaker, you have all these zinc atoms that are a part of the solid, that's the single element, and then you have these copper ions that are a part of the solution, the aqueous solution, and there's also sulfate floating around in here. But what's going to happen is the copper is going to replace the zinc, or the zinc is going to replace the copper, I mean. So what you saw build up on that strip of metal was all of the copper ions that were sticking to it. And what you couldn't see were the zinc atoms that were coming out of that strip and becoming part of the solution, because the zinc is more reactive than the copper. So that what looked like a black film that was developing on that metal was actually copper going from being ions to being solid copper. Okay, let's take a look at another equation. We're going to show you how we predict what the products would be. So here are my reactants. I have solid lithium that is going to react with a lead 2 nitrate solution, or aqueous lead 2 nitrate. It's dissolved in water. So the first question we need to ask ourselves is, which element is trying to replace which element? The lithium is going to attempt to replace the lead because lithium is a metal, and it's going to replace the other metal, the lead. Can this replacement happen? Well, we need to look at that table. If we look here, here's lithium, and here's lead. So lithium is much more reactive than lead, so it will be able to replace lead in this reaction. Okay, so can the replacement happen? Yes, it can. Lithium can replace lead. So then we need to ask ourselves, what will the new product be? And it's not quite as simple as just swapping these two, and I'll show you why. When we form new products, there's a couple of things we need to keep in mind. We have to determine the charges of all of the ions involved so that we can make a new compound that is electrically neutral. We did this back in chapter 7. We have to make sure that our positives and our negatives cancel each other out, okay? So I'll show you what I mean by that. The charge of lithium, if you look on your periodic table, lithium is a +1. Lithium is going to replace lead and bond with the nitrate. Nitrate is a -1. So lithium's a +1, nitrate's a -1, so we just need one of each to make that compound. Let me kind of lay that out here for you. Here's lithium's charge, +1. Lead in this case is a +2. We know that because it's combined with 2 nitrates, each are -1. So I have a total -2 charge, so that makes this a +2. And then, as I mentioned before, nitrate is a -1. If I'm going to combine my lithium with my nitrate, +1, -1, I just need one of each. So it's going to form LiNO3. Notice, there were 2 nitrates on this side. That's because lead was +2 and I needed 2 of them to make it neutral. But I only have 1 nitrate on this side because lithium is a +1, so I only need 1 nitrate. And then the lead gets kicked out and is the single element. Please note, this equation is not balanced. There are 2 nitrates here, there's only 1 here. We will balance equations later. I'm not really concerned about doing this at this point. We're just going to make sure we can write the products correctly. Okay, so we have single lead and lithium nitrate solution. Let's take a look at another one. I have lead that is combining with iron 2 chloride. So once again, those questions I need to ask myself. Which element is trying to replace which element? Lead is going to try to replace iron, the other metal. Can this replacement happen? Take a look at that table and see if lead is more reactive than iron. Here's lead. Here's iron. Lead is not more reactive than iron. So, can the reaction happen? No, the replacement cannot happen because lead is not more reactive than iron. So we would just simply write it like this, no reaction. Now, let's take a look at an example where our single element is not a metal, it's a nonmetal. We have chlorine, which is diatomic, so it's written as Cl2, combining with sodium iodide. So we have to ask ourselves again, what element is trying to replace what element? In this case, chlorine is going to attempt to replace iodine. This is a nonmetal, it can only replace the nonmetal. Now, can the replacement happen? Nonmetals are not listed in that reactivity series that I gave you before. I have down here the halogens. This is group 7 on the periodic table. These are pretty easy to remember because they're the most reactive ones are at the top and they get less reactive as you go down. So fluorine is the most reactive nonmetal and it moves down the column. They become less reactive. So in this case, chlorine is trying to replace iodine. Chlorine is more reactive than iodine, so the replacement can happen. So then we have to ask ourselves, what will the new product be? In order to do that, we have to consider the charges. Okay, so determine the charges of all of the elements. Chlorine forms a -1, sodium is a +1, and iodine is a -1. So then when we put them together to make a compound that is electrically neutral, it will look like this. Here are the charges. Chlorine's a -1, sodium's a +1, iodine's a -1. So if I'm going to combine the sodium with the chlorine, +1 -1 means I need one of each. That's sodium chloride. And then the iodine got kicked out, and that's the single element. Couple things. Iodine is also diatomic, which means you can't just write I, it has to be I2. Okay? And chlorine, while it was diatomic here, is not diatomic here. It's combined with the sodium, so you don't put that 2 there. Okay? That's only if it's by itself. When it's combined with sodium, it has to be electrically neutral. +1, -1. All right. This single replacement reaction that I'm going to show you here is incorrect. I would like you to take a look at this and see if you could determine why it's incorrect. We're going to run through the same steps that we would always run through to determine what the product should be. First of all, if you look at the reactants, which element is trying to replace which element? In this case, my single element is fluorine. Fluorine is a nonmetal, so it will try to replace the nonmetal in the compound. And the nonmetal in the compound is the bromine. So fluorine is going to try to replace bromine. The second question we have to ask ourselves is, can this replacement happen? In other words, is the fluorine more reactive than the bromine? If you look at that list of halogens on your periodic table, fluorine is the most reactive nonmetal, so it is more reactive than bromine and it can replace it. So the next thing we need to do is we need to figure out what the new product should be. So let's take a look at the charges of all of the ions. Lithium is a +1, bromine is a -1, and fluorine is a -1. So what should the new product be, the new compound? The new compound should be lithium combined with fluorine, the positive with the negative, +1, -1, so it should be LiF, and then bromine should be the single element by itself. So here's what that reaction should look like. Fluorine is attempting to replace bromine. Fluorine is more reactive than bromine, so the reaction will happen. Lithium is a +1, bromine's a -1, fluorine's a -1. So here is what the product should look like. LiF dissolved in water plus the bromine. Notice bromine is one of the diatomics, so it's written as Br2, not just Br. Once again, these equations are not balanced. So you'll notice there's 2 fluorines on this side and there's only 1 fluorine on that side. It's okay for right now. We got to get the equations written correctly before we can balance them. All right, so I am going to give you some reactions and I'm going to ask you to answer some questions about these reactions.